What's up, everybody? In this video, we're going to cover USACO's 2018 US Open Contest problem at the silver level. Number 2, lemonade line. Let's read together. It's a hot summer day out on the farm, and Farmer John is serving lemonade to his N cows. Okay, so that's how many cows he has. He has N cows. All N cows conveniently numbered 1 through N. We get that a lot. Basically, when you have N cows numbered 1 through N, then you have like 1, and you have 2, you have 3, and that goes all the way up to whatever N happens to be. So if N is 5, if we've got 5 cows, the numbers are 1, 2, 3, 4, 5. There are no duplicates and there are no missed numbers. All N cows like lemonade, but some of them like it more than others. In particular, cow I is willing to wait in line behind at most WI cows to get her lemonade. Okay, so looking at these symbols, it's important to pay close attention to these symbols. Don't let them intimidate you. Basically, we've got cows numbered 1, 2, 3, 4, and so forth. And then each cow is willing to wait some amount of time. Cow 1 is willing to wait for W1 time. Cow 2 is willing to wait for W2 time. So it's just a way to identify the numbers. However, whatever the time is, for example, if cow 1 is willing to wait 7 seconds, then W1 is 7. So then later when they say cow I is willing to wait at most WI, what they're saying, for example, is this is cow 1 equals 7, then W1 would be 7. If I is 2, meaning cow 2, then WI would be however long cow 2 is willing to wait. WI cows to get eliminated. Right now, all N cows are in the fields, but as soon as Farmer John rings his cowbell, the cows will immediately descend upon Farmer John's lemonade stand. They will all arrive before he starts serving lemonade, but no 2 cows will arrive at the same time. Okay, so the cows are going to come in some sort of a random order. Furthermore, when cow I arrives, remember we talked about when any given number cow I arrives, she will join the line if and only if there are at most WI cows already in the line. Right, so if cow 1, let me rewrite this here. If cow 1, for example, if I is 1 and then WI is 7, that means that cow 1 will only stand in line if there are 7 or fewer cows in front of her. So the waiting amount is not in terms of time, the waiting amount is in terms of cows. So Farmer John wants to prepare some amount of lemonade in advance, but he does not want to be wasteful. The number of cows who join the line might depend on the order in which they arrive. Help him find the minimum possible number of cows who join the line. Okay, so what that's indicating is that there's certain arrangements where more cows will join the line and certain arrangements where fewer cows will join the line. In order to not be wasteful, he's going to make the smallest amount of lemonade that he can guarantee will get used. So whatever the worst possible arrangement is that leads to the fewest cows getting in line, that's how much lemonade he's going to make. So that's what we're trying to optimize for. All right, input format comes from the file lemonade.in. You're going to have to make a file reader. The newer problems I'll read from the console, but the older ones require file readers. The first line contains N, right? Okay, so for example, 5. And the second line contains the N space-separated integers W1 through Wn. So this is 7 is W1, W2, W3 is 400, W4, and W5. And that's just the time that each cow is willing to wait. 2, W3, W4, W5. 7, 1, 400, 2, and 2. So if we're saying like, okay, what about cow I if I is 4? If I is 4, then cow number 4 is willing to wait in 2 seconds. You'll also notice these aren't in any specific order: 7, 1, 400, 2, and 2. It is guaranteed that 1 is less than or equal to n, which is less than or equal to 10 to the 5th. 10 to the 5th, that's a big red flag. If you have 10 to the 5th, if you have 10 to the 5th, you cannot square that, because if you were to square that, you'll have 10 to the 10th. 10 to the 10th is 10 billion, and 10 billion is too large of a problem to pass time complexity. Unless specifically noted in the problem. I think there's been 1 or 2 problems where they extended that. For the most part, if you hit 10 to the 10th, you've gone too far. So we can't square it, so we need a linear algorithm or a n log n algorithm. And that 0 is less than WI is less than or equal to 9, 10 to the 9th. 10 to the 9th is a billion. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's okay. That just lets you know that the amount that they're willing to wait, the integers here, will not be more than a billion, which means we don't need to use longs. We can use conventional integers. Output format is written to the file lemonade.out. Make sure you're actually writing that to the file and closing the file and not just printing it to the screen. Print the minimum possible number of cows who might join the line among all possible orders in which the cows might arrive. Okay, so the important thing to note here is, let me see, we're gonna draw, let's put Farmer John's little lemonade stand. I'm gonna do like this, lemonade, 5 cents. Get the Charlie Brown thing going on. Here's Farmer John, whatever, and then he's selling lemonade. Okay, so we're gonna have the cows line up. Now the cows could line up in any kind of order. Here's a cow, 2, 3, 4, and 5, and I'm gonna draw numbers on them. Cow, cow, cow. Okay, so first cow arrives. For example, what if cow 2 was the first one to arrive, or cow 4, which has a waiting time of 2, was to arrive? Then this cow who's willing to wait for 2 cows would get into this location in line. Because there are not 2 cows in front, then that cow is perfectly happy there. Let's say like the next cow to arrive would be the cow that's willing to wait for 7. So we have fewer than 7 cows in line in front, because we've only got 1 in line so far. So cow 7 is willing to wait in line because there's only 1 cow in front of them. Next cow maybe could be the cow that's willing to wait for 1. The cow that's willing to wait for 1 arrives, but upon seeing that there's more than 1 cow in line, this cow steps out of the line, leaving an open space there. So this cow is going to go over here, but then this spot remains available. There's no cow there yet. This cow right here arrives. Cow is willing to wait for 2. Here's 2 cows already in line. So this cow will line up behind, and that's totally fine. Notice not having to line up behind the 1 cow. The 1 cow stepped out of line because they weren't willing to wait. The 2 cow then is able to take that place. That place is not occupied by 1. And it's important to note that, and I'll point out why in a minute. And then finally 400. 400 is willing to wait for 400 cows. Oops. So they line up 400. And that means that in this particular arrangement, I got 4 cows to stand in line. Now, they're telling us that there's an arrangement where only 3 cows will stand in line. Let's see if we can put them in a optimal arrangement, and what would be the most and what would be the least. So an optimal arrangement, if I wanted the optimal arrangement, I would put the least patient cow in the front, because then that has the highest chance of them getting served. And the next least patient cow, and the next least patient cow, and then the next one, and the next one. Now, if the cows lined up in this order, this cow would be willing to wait because there's fewer than 1 cow in front. This cow only has 1 in front, so they're fine. This cow has 2 cows in front, so she's fine as well. 7th cow has only 3 in front, and then the 400 only has 3 in front. So in this case, all 4 were able to get the lemonade. Let's reverse the order and watch what happens. If I put my most patient cow at the front and my least patient cow at the back, then that increases the chance that cows are going to get out of line, that this cow is going to leave. So if I go 7, and then 2, and then 2, then I've got my most patient cow waiting in the front of the line here, and then a little bit less patient, a little bit less patient, a little less patient, and the least patient cow. Now the 1 cow is not going to be willing to wait. This cow has 3 in front of her, so she's not going to be willing to wait. The cow in the position here, 2, only has 2 people in front, so they're willing to wait. That ends up being 3, and that is in fact the output. All right, now let's look at a different test case. I'm going to see what would happen if we were to change one of these numbers to a 5. So we're going to do 400, 7, 5. Let's do 3. Let's actually do 3. 3, 2, and 1. Okay. So if we have them arranged like this, and we go from largest to smallest, I have 400 in the front, 7, 3, 2, 1. Okay. So this one is willing to wait, obviously. This one's willing to wait as well. This one would wait for 3. These 2 will not wait in line. That ends up being a maximum of 3. Now let's look at the ordering, because you might look at this and think, well, what would happen if cow 3 were to move back in the line? We want to try and get the minimum number, and right now I've got 3 cows getting served. If I were to move 3 to the back of the line and let 2 and 1 move up, like so, 2, 1, and 3, at first look, it seems like only 2 cows are going to get served. It seems like only the 400 cow and the 7 cow are going to get served. But then let's actually rearrange this. Let's go like this. 1, 2, 3. Okay. So it looks like only the 400 and the 7 cow are going to get served, and that this cow here in the 3rd position that's willing to wait for 1 cow only is not going to wait in line. This cow will not wait for 2, and this cow will not wait for 3. So it seems like we found a more optimal solution where only 2 cows get served. But what's going to happen is because cow 1 isn't willing to wait, they're going to get out of line. And then cow 2 also would not be willing to wait. Actually, cow 2 then would be willing to wait. Cow 2 would wait for this person, and this cow and this cow. So they would wait, and then 3 would wait. And that ends up giving us an answer of 4. If I arrange this in a different ordering, I had 1, 2, or I had 1, 2, and 3. If I put the 3 here, and the 2 here, and the 1 here, which is in reverse order, then this cow right here is not going to wait. This cow is going to wait, and I've got 3 cows still. And I can't find a situation that gets 2, and I can find situations that do more cows. I can find ways to get more cows in line. And if I were to switch these orders right here and have this be 2 and this be 3, I could get more cows, but I can't do anything to get fewer cows. The only way to get fewer cows is to have them in as much close to reverse order as possible. If you have them in reverse order, then essentially you're guaranteed that as you're working your way through, the least patient cows are at the back, which means the least patient cows are most likely to get out of line. As far as coding this, your coding solution actually ends up being fairly straightforward. What you're going to have is your list of numbers. Let's look back at the sample case here. 7, 1, 400, 2, and 2. We sort them in decreasing order. So 400 will be first, and then 7, and then 2, and then 2, and then 1. So our least patient cows are at the back, our most patient cows are at the front. Then what we do is we just compare everything to its index. The cow that's in the front would be willing to wait for, the cow that's in the front only has to wait for 0 cows. The second cow has to wait for 1 cow. The third cow has to wait for 2 cows. The fourth cow has to wait for 3 cows. And the fifth cow has to wait for 4 cows. Their position tells how many, the index actually tells how many cows they have to wait for. So second cow in line, index 1, will only line up if there's 1 cow in front at most. And since this is index 1, the 1 is how many cows are in front. So if this cow is willing to wait for 7 and there's 1 in front, we're okay. This cow is willing to wait for 2 and there's 2 in front, and we're okay. This cow is willing to wait for 2, but there are 3 in front. So 1, 2, 3, which means that as soon as you encounter a cow who is willing to wait for fewer, strictly less than the number of cows in front of them, that cow is not going to get in line. And every cow after, since we are sorted from most patient to least patient, every cow after is guaranteed to be even less patient than the cow in front of it. So because of the fact that we know that the 2 isn't going to be willing to line up, anything that's going to take this place right here is going to be either equal or lower. In this case, 1, which also is not going to line up. Since we are guaranteed that everything to the right is less than, as soon as we encounter a situation where I've got a cow whose patience is less than the number of cows in front, I stop. And whatever index that is, that's how many cows are in front of that cow, which then is how many cows are going to get lemonade. So essentially, all you need to do is take your list of numbers, sort them in decreasing order, 400, 7, 2, 2, 1, and then walk through looking at the index, 0, 1, 2, 3. As soon as your index gets larger than the patience level of the cow, you report that as your answer. Alrighty, good luck coding it, and I'll talk to you in the next video.